Direction cosines for lines not passing through the origin. To start, let's quickly recap what we've already covered. In our previous subsection, we learned how to define direction cosines, or DCs, for a line that specifically passes through the origin. That was a great starting point, but it was a bit of a simplified case. The reality is that in three-dimensional geometry, most lines you encounter won't necessarily pass through the origin, which is the point 0, 0, 0. Because these lines are shifted away from the center of our coordinate system, we can't use that same direct method. So, in this section, I am going to show you exactly how we determine the direction cosines for these more complex lines. By the end of this lesson, you'll see that the process is much more intuitive than it might first appear. Welcome, everyone. Let's begin our new session. Now, if you look at the title of today's lesson, we are focusing on direction cosines for lines that do not pass through the origin. Understanding the concept. The most important thing to realize, and I want you to really keep this in mind, is that direction cosines describe the orientation, or the tilt and slope, of a line rather than its specific position in space. Think about it. If you have a line, let's call it L, that does not pass through the origin, you won't be able to directly measure those angles alpha, beta, and gamma from the origin point itself. This creates a problem because our standard method for finding direction cosines relies on that origin point. To solve this, we are going to use a fundamental property of parallel lines. In Euclidean geometry, we know that two lines are parallel if they share the exact same direction. Because of this, if two lines are parallel, they will make the exact same angles with the x, y, and z axes. And since those angles are identical, it follows logically that they must also share the exact same direction cosines. Now that we've established that we are moving beyond lines that simply pass through the origin, let's focus on the core concept here on slide 2. This realization is the bridge that allows us to take a line anywhere in space and treat it as if it were passing through the origin, which is the step-by-step process we are about to see in the next slide. Step-by-step process to find direction cosines. First, you need to identify the line. You'll start with your given line, which we'll call L. Remember, at this stage, this line could be floating anywhere in our three-dimensional coordinate system. It doesn't have to be near the center. Second, we are going to construct a parallel line. This is a mental or visual step. We are going to imagine a second line, let's call it L', that is perfectly parallel to our original line L, but with one specific difference. We are going to anchor this new line, L', so that it passes exactly through the origin, which is the point 0, 0, 0. Third, once we have this new line passing through the origin, we can determine the angles. Because L' is anchored at the origin, it becomes much easier for us to measure the specific angles, alpha, beta, and gamma, that this line makes with the positive directions of the x, y, and z axes. Fourth, we calculate the cosines. Once you have those angles, you simply find the cosine of alpha, the cosine of beta, and the cosine of gamma. Finally, the fifth step is to assign these values back to the original line. Since we established in the previous slide that parallel lines share the same orientation, the direction cosines we found for our new line, L', are exactly the same as the direction cosines for our original line, L. Now that we understand the core concept, that direction cosines are about orientation rather than position, let's walk through the actual procedure you'll use to solve these problems. I've broken this down into a 5-step process. To make this even clearer, let's look at a real-world analogy in the next slide. Real-world analogy. Now, to help you truly grasp this concept, let's step away from the coordinate planes for a moment and use a real-world analogy. Imagine you are walking through a park, and you see a flagpole standing perfectly vertical. Now, think about its position. This flagpole is located somewhere in the park, but it certainly does not pass through the center of the city, which we can think of as our origin. Next, I want you to imagine a second flagpole. This one is placed exactly at the center of the city, right at the origin. This second pole is also standing perfectly vertical. Because both poles are standing straight up, they are parallel to one another. If you look at them, both poles make an angle of 90 degrees with the ground, which is our xy plane, and both are parallel to the z-axis. The key takeaway here is that regardless of where that first pole is located in the park, its direction, its tilt, or its orientation is exactly the same as the pole located at the origin. This is exactly how we approach our mathematical problem. We look at the direction, not the location. Now, let's see how this applies to a concrete mathematical example in the next slide. Illustrative example. Here we are presented with a problem. We need to find the direction cosines of a line. Let's call it line L, which is known to be parallel to another line that passes through the points P, with coordinates 2, 3, 4, and Q, with coordinates 5, 7, 10. First, we need to find the direction of the line segment PQ. To do this, we calculate the vector PQ. We find this by subtracting the coordinates of the starting point P from the coordinates of the ending point Q. So, for the x component, it is 5 minus 2. For the y component, it is 7 minus 3. And for the z component, it is 10 minus 4. This gives us a direction vector of 3i hat plus 4 j hat plus 6k hat. Second, we apply the core concept we discussed in the previous slides. Even though our original line L might be anywhere in space, we can imagine a new line, L', that passes through the origin 0, 0, 0, but shares this exact same direction vector, 3i hat, 4j hat, and 6k hat. Third, we need to calculate the magnitude of this direction vector. To convert these direction ratios into direction cosines, we must divide by the total length of the vector. So, we take the square root of the sum of the squares of our components. That is, the square root of 3 squared plus 4 squared plus 6 squared. Calculating the squares, we get 9 plus 16 plus 36, which totals 61. So, the magnitude is the square root of 61. Finally, we can calculate the actual direction cosines, which we denote as L, M, and N. We simply take each component of our vector and divide it by that magnitude we just found. This gives us L equals 3 over the square root of 61, M equals 4 over the square root of 61, and N equals 6 over the square root of 61. And remember, because the original line L is parallel to this direction, these values are precisely the direction cosines for our original line L. Now that we have understood the theory and the concept of using parallel lines, let's put everything into practice with an illustrative example. Let's walk through the solution step by step. As we move to the next slide, we will summarize the key takeaways from this entire lesson. Key takeaways. First, remember the principle of position independence. This is a crucial takeaway. Direction cosines are entirely dependent on the orientation or the tilt of the line. They do not care where the line is located in space. Whether the line passes through the origin or is tucked away in a far corner of the coordinate system, if the tilt remains the same, the direction cosines remain the same. Second, we must emphasize the role of parallelism. As we discussed earlier when looking at the flagpole analogy, parallel lines are essentially copies of each other in terms of direction. Therefore, any two lines that are parallel will always share the exact same direction cosines. Finally, let's recap the method we've learned. If you are faced with a line that does not pass through the origin, do not let that intimidate you. Your strategy should be to conceptually shift that line back to the origin. By creating a parallel line that passes through 0, 0, 0, you can easily identify the angles and calculate the cosines, knowing that these values apply perfectly to your original line. Now that we have worked through our example, let's pause and summarize the most important points from today's lesson to ensure you have a solid grasp of the concept. In our next session, we will look at how to avoid some common pitfalls that students often encounter when working with these calculations, so please keep these core principles in mind. Common mistakes. First, let's talk about the mistake of confusing position with direction. This is a very frequent error where a student takes the coordinates of a single point on the line and mistakenly uses them as the direction cosines. Please remember what we discussed in our very first slide. Direction cosines describe the tilt or the orientation of the line, not where it is located in space. A point, such as x, y, z, actually gives us a position vector, which is a vector starting from the origin and ending at that specific point. However, the direction of the line itself is determined by the displacement between 2 points, or by a given direction vector, much like the vector PQ we calculated in our example. Second, be very careful not to forget the magnitude. When you are given direction ratios, for instance, the numbers 3, 4, and 6 that we used in our illustrative example, you cannot simply call those your direction cosines. You must first find the magnitude, which is the square root of a squared plus b squared plus c squared, and then divide each ratio by that magnitude. Always perform a quick mental check. Your final direction cosines, L, M, and N, must always satisfy the condition that L squared plus M squared plus N squared equals 1. If your sum does not equal 1, you know you have missed a step. Now, before we wrap up today's lesson, I want to touch upon some common pitfalls that students often encounter when working with direction cosines. It is crucial to address these so you can avoid losing marks in your exams. Keep these points in mind, and you will find much more success with 3D geometry.